We're going to continue on here, chapter 13, I think. So we're talking about carbohydrates. And remember, basically, we have monosaccharides, and they will have, again, one of two functional groups up on top. They will have the aldehyde group, which makes it an aldose type of carbohydrate. They may also have up towards the top there a ketone type of group. And again, kind of looks something like that. And this one, because they have a ketone group, sometimes referred to as a ketose. We could also count up the carbons and kind of classify it based on the number of carbons there is. Pentose for 5, hexose for 6, triose for 3. We talked about L and D, and remember that L and D refer to basically the last hydroxide group, OH group, and sort of which side it's on. If it's on the right-hand side, it's a D. If it's on the left-hand side, it's an L. And it is the last chirocarbon from the top, or sort of the functional group here on these guys. Remember that, again, a chirocarbon is one that has basically 4 different groups attached. Again, as we saw, and in a lot of cases, that last chirocarbon, not 100% of the time, but a lot of times is kind of like one back from that bottom CH2OH. And again, that sort of OH, if it's on the left or right, as to L or D. We talked about turning our sort of straight chain carbohydrate, if you will, into a cyclic structure. And once again, um, the idea of sort of how to do that we talked about. And really, this will usually give you one of two sort of cyclic rings when they do it. One looks very much like cyclohexane, except it does have 5 carbons because there's an oxygen that gets incorporated into that ring. So again, it will look very much like cyclohexane, but again, it only has actually 5 carbons there because of that oxygen kind of takes the place of a carbon. The other one is really one that looks like cyclopentane, but actually has 4 carbons for the same reason. Again, the oxygen gets sort of incorporated into the ring as they close. Now, what happens when we want to kind of draw these guys into the cyclic structure? Again, we can number the carbons, and that functional group is always sort of carbon number 1, number 2, number 3, number 4, number 5, and number 6 in this case. And in the case of sort of a 6-carbon carbohydrate, it's always going to be carbon number 5 there, and it will always really go and find the carbon-oxygen double bond, so wherever that may be. Usually it's the last chirocarbon that goes and does that if there happens to be less than 6 carbons in that situation. But it'll always find that carbon-oxygen double bond. That means as well, if you have more of the ketone group up on top, whatever carbon is coming in is going to go actually to carbon number 2 in that case, and that's what's going to close up the ring. We could also count up at that point sort of how many carbons we should draw in our ring. We'll have 1 carbon, 2 carbons, 3 carbons, 4 carbons, and a 5-carbon ring that's part of it. So we would go with this guy as our sort of structure here. Remember that this sort of carbon number 6 always ends up to the left of the oxygen in the ring, or that last sort of carbon, that's usually that CH2OH at the bottom, will always end up basically to the left of that oxygen. That also gives us a location of numbering. That's going to be 6, and then we're going to go counterclockwise 4, 5, 4, 3, 2, and 1 in this case. And again, you could either drop it on its side and redraw it, or as we talked about, basically, again, if you drop it on its side, everybody on the right-hand side will end up down, and everybody on the left-hand side, as it's kind of coming over, will then end up in that situation. And that's really what's going to allow us to kind of know where to put the OH groups on the ring. In this case, we do skip the 5 carbon here because that's pretty much right here where it kind of gets incorporated into the ring. So we would go number 4 and we would see the OH there's on the right-hand side, which means the OH should go down on the ring. We'd go number 3 there, and the OH that I didn't draw, so I did it over here. The OH is over there on the left-hand side, which means it should go up. Number 2 there, OH is on the right-hand side, which means it should go down. Now, the last OH here is determined on sort of what you're asked to draw, and you'll be asked to draw either an alpha or a beta, and basically that kind of tells you sort of which way you should put the OH. If it is alpha, the last OH will go down. If it is beta, the last OH will go up. So if we were going to do the alpha in this case, we would put the last OH over here. And then we would have obviously our cyclic structure in this case. Any questions on that? I think it was a question last time, and just the reason again we do skip sort of carbon number 5 is this oxygen here gets incorporated right there, and basically this hydrogen actually slides over here to the oxygen there, and that becomes a single bonded, and that ends up, right there basically. And that's why, again, we kind of skip 5 because that kind of guy gets incorporated in the ring, which really where that sort of carbon and oxygen double bond is located. Any questions on that stuff there? All right, then let us continue on here. So obviously you can have alpha D glucose or beta D glucose, and really the only difference here is between the alpha and the beta is the location here, the OH group, and again alpha coming down and beta coming up. And you can see that 64% of it is beta and 36% is about alpha. And it will kind of open and close to do that. So sort of constantly opening and closing the ring. There's only a small amount of the open chain there. It's in that process of it kind of either opening and kind of closing back up in one of these configurations. Now, fructose, and we drew one similar to this, again, in this situation, because it is the ketone group that is there, we are going to again go from this carbon right here, and if we numbered them 1, 2, 3, 4, 5, and 6, and it will go again to carbon number 2 where the carbon oxygen double bond's located. That again is going to give us a different ring, and again I think we drew one the other day similar, but we count up our carbons 1, 2, 3, and only 4 carbons are going to be within that chain, and that's going to give us that one that looks more like cyclopentane, which has 4 carbons in there. Again, going to work the same way. The only difference here is we will end up with, as we kind of saw in that example I think we did the other day, we'll end up with actually 2 groups that are not part of the ring, and still carbon number 6 in this case will end up over here like normal. The other group that is off the chain will end up there on the last carbon, and again, depending on what you're asked to draw, alpha or beta, the OH will go down for alpha, the OH will go up for beta, and if the OH goes up for beta, that means that last kind of carbon CH2OH group will go down in the opposite location. A reminder as well, usually not drawn on the other side of these guys are the hydrogens. So those are all, again, hydrogens, so it doesn't get so crowded. But again, in that situation, is still the alpha and beta determines where the OH is. The only difference is on the other side, you won't have a hydrogen. You'll have that CH2OH group that's attached there. Any questions on that there? All right, so why don't you draw this one into a cyclic form, see what you come up with. Okay, so let's take a look. So again, we're gonna kind of number our chain here. So 1, 2, 3, 4, 5, and 6 in this case. So once again, we're going to go here, carbon number 5. It's going to go find the carbon-oxygen double bond. And again, if we just count up the carbons between those, 1, 2, 3, 4, and obviously 5 there, that's going to tell us again that we need the one that looks like cyclohexane, our 5-carbon sort of ring. Once again here, our number 6 is always going to go to the left of the oxygen up on top. And again, if we kind of number 6, 5, 4, 3, 2, and 1 in this case. And once again, as we talked about, you can either redraw it on its side or just again remember right hand side is going to be down, left hand side is going to be up. So we'll go to number 4 here as we skip 5 as it gets incorporated into the ring, and we're on the left hand side. So once again, when it drops, it's going to be up. As I missed number 4 there, but kind of close. We'll go to number 3 there, which is also on the left-hand side, and it's going to go up. And number 2 here is on the right-hand side, which again means when it falls on its side, it's going to go pointing downward. Again, our last one there at number 1 is going to be determined by what they asked us to draw, which was the alpha anomer in this case. And that means alpha means that we'll put the last OH pointing downward here. Any questions on that? Yeah. Yeah, so in terms of the ring that we draw, it's based on kind of all the carbons to get caught between number 5 and number, in this case, where the carbon oxygen double bond is. So we started here, so this carbon gets into the ring. This guy is kind of trapped in the middle, so it gets in the ring. This one does, and this one will all get incorporated into the ring. And that's why in this ring, even though it looks like cyclohexane, we actually only need 1, 2, 3, 4, and 5 carbons. Those are the 5 carbons to get in there. So this group here, that's really not part of the ring formation. This group here gets sort of left out, and it ends up there, up on top. So we don't really need any extra carbons in this case because we have basically enough in the ring that we drew in this particular case. Are you talking about the CH2OH? Yeah, so because it kind of gets left out in the cold there when it kind of closes, those 2 carbons is kind of outside. It does become kind of like a group attached to the ring rather than incorporated into the ring. And as I mentioned a second ago, in terms of carbon number 5, um, this oxygen here actually ends up right there. And this, we'll go red. This hydrogen actually switches and ends up over here. It actually comes up and kind of attaches to that oxygen. And that's where the OH group comes from. That's on the very end. At the end, there's the oxygen on top, and that hydrogen, it slides over. Basically, it makes the OH group that ends up being this guy here is from here and here, those 2 guys. Yeah. Was there a question behind you? Yeah or no? No? Okay, you good? Yeah, fine. Okay. Yeah. We'll talk about it at the end for sure. Yeah. But it will have these chapters, but it'll have everything, to be honest with you. So it'll be pretty equally spread out, I think, over everything that we talked about this semester. Yeah. All right. Other questions? All right. So there was kind of a question about, what happens maybe if you were given a ring and it sort of opens up. So if you wanted to sort of go in the other direction, I'll just draw a made up one here. We'll just do that. We'll do that. And we'll do this. So let's just say we wanted to like open the ring and kind of put it back into this straight function. So the first thing that you would want to do is really just count up the carbons you got going on. And again, here we got definitely 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons, and 6 carbons total. And we know that when we kind of look at it like this, we number usually the ring in this direction: 6, 5, 4, 3, 2, and 1. So just like we kind of are making the ring, it's the same way we number it. So we definitely know that our kind of straight chain one there is a six carbon chain. We also can make a pretty good guess that this is going to be an aldehyde group up on top because as we saw with fructose there and a ketone group, we would have an extra carbon hanging off there, right? Which we don't have in this case. So we basically have the closing of the ring to the very top, and we don't have any other carbon group that's not part of the ring. So you can feel pretty safe because you don't see a carbon group here, like a CH2OH, not there. That is most likely going to be the aldehyde. If you did see a CH2OH group there, then you could probably be pretty confident that you're dealing with a ketone up on top because that's basically, as we kind of saw with fructose, that's basically kind of what happens in that case. At that point, you could kind of just draw the rest of your carbons, so 2, 3, 4, 5. And we know that this guy is going to be carbon number 6 here, right, which is this guy. And then numbering, we know this is going to be 1, 2, 3, 4, and 5. So we basically now have sort of our structure if we wanted to open this thing up. And really, we kind of do exactly the same deal as we did when we put the OHs on, right? So when we put the OHs on the ring, if it goes down, that means it originally was on the right-hand side, right? And if it went up the OH, it was originally on the left-hand side. And we just kind of do that backwards. So if we go to carbon number 2, I have an OH group that's facing up, which means it would have to be on the left-hand side, right? Again, when it drops, it will be facing up, right? So going backwards, it's got to go back to the left-hand side. If I go to carbon number 3, I see my OH is pointing down, which means it would has to be on the right-hand side because again, when it drops, it's going to be pointing downward like it is in the ring. And that means number 4 here should also go to the right-hand side. And once again, the other side of this is really going to be hydrogens. So I now have pretty much my entire structure opened. The only thing I'm missing is carbon number 5, right? And carbon number 5 gets incorporated right there. So we do need some help to understand how we should draw carbon number 5. So just like when you're asked to draw the ring structure, they tell you draw either alpha or beta. If you were to open it, you would be asked to draw either L or D, right? And what does that mean again? L means the last OH group would be on the left, and the last OH group would be on the right if it was D. So if they asked you to draw the L version of this, we would then know that is where we should put our last OH. Whoops, as it disappears. And obviously, if we were asked to draw the D version, we would put the OH on the other side. So if you did want to open the ring, again, you basically just kind of work backwards based on where the position of the OHs are on the ring. If they're pointing up, they go back to the left-hand side. If they're pointing down, they go back to the right-hand side. And again, that last carbon will usually be determined by what you're asked to draw, either L or D. Any questions on how to open it? Yeah. Yeah. All right. When it makes the ring, this this hydrogen here actually that's part of the OH. It's not this hydrogen, it's actually this one right here. That is the one that actually slides up and kind of bonds into the oxygen. And that's really what generates the O and the H that we end up with. It ends up way over there. There's a lot of steps in between that, but the short answer is it slides over and basically bonds to the oxygen to do that. And that happens a lot in organic chemistry. Sometimes hydrogen's just going to slide to a different location, and that's sort of what ends up happening in this particular. Other questions? All right, questions on how to draw these here. I would probably focus my efforts on this way. Yes, if I was a guessing person. Yes. All right. All right, then let us continue on here. The next thing we're going to talk about are some properties of monosaccharides. And monosaccharides are sometimes referred to as reducing sugars. And reducing sugars are monosaccharides that have that carbonyl group. And again, the carbonyl group is the carbon oxygen double bond. and it oxidizes to make our carboxylic acid. So it will undergo a reaction with Benedict's reagent and for the corresponding carboxylic acid. This is the exact same oxidation of aldehydes that we saw in organic chemistry. If you have an aldehyde and you oxidize it, that throws an oxygen into that spot, and you end up with our carboxylic acid, just like we saw in organic chemistry. And the same thing happens with the sugars because they have basically the same organic functional group hanging out there on top, and it's able to do that. So pretty much most sugars are reducing sugars. They include the monosaccharides, glucose, galactose, and fructose. There's a disaccharide that can't do it, and we'll take a look at it in a bit. But most sugars could kind of be a reducing sugar, and that's what we see here with Benedict's reagent. It's going to cause again the oxidation to occur. Is going to throw our OH in there, and that is going to make our carboxylic acid. And obviously, just like we talked about in sort of organic chemistry, that would yield you a positive test for Benedict's reagent, which is positive for carboxylic acid formation, right? That happens from an aldehyde to to a carboxylic acid. Does not happen on a ketone. It does not get oxidized, right? So it's able to do so. All right. We won't worry about those. You're not going to have to draw it, so don't worry about this. All right, then let's talk a little bit about disaccharides. Disaccharides are basically two monosaccharides that are put together. They're basically put together by taking water out and making a bond between the two carbohydrates. Now, there are three types of disaccharides we can talk about. There's maltose, lactose, and sucrose, and we are going to look at each of these individually here. But maltose is made up of two glucose molecules. Uh, Glucose and a galactose coming together will make lactose, and glucose and fructose will make sucrose. There's uh, here. So you do need to know the three disaccharides, and you do need to know the monosaccharides that make each of them up. So that's probably good. So let's take a look at each of these. First off, we have maltose, and maltose is a disaccharide known as malt sugar. It is basically composed of two D-glucose molecules, and it's obtained from the hydrolysis of starch. It is linked by a specific bond, which is sometimes referred to as a glycosidic bond. It is what is referred to as an alpha 1,4 glycosidic bond. And we're going to take a look at it in just a second. But basically, it is the linkage between the two carbohydrates, how they kind of hook together when water is removed. And it is very descriptive, basically, the alpha and the 1,4. The alpha 1,4, the numbers basically indicate the carbons where they connect together. And alpha, as we know, means downward. So that is what's happening there. This is what is used in cereals, candy, and brewing. And it does happen in the alpha and beta form of it. So if we take a look here, these are our two glucose molecules here. And the connection is going to happen at carbon number 1 on this glucose and carbon number 4 on that glucose. And that is the origin of the 1,4 part of the bond. It is when we take a look at carbon number 1, that OH is in the alpha position, which is where the origination of the alpha 1,4 part comes from the name of this glycosidic bond. So basically what's going to happen in this case is we're going to bond these guys together and we are going to take out water. H2O is basically going to come out. And if you count up all the letters there, I got two hydrogens and two oxygens, which means I'm going to be left with one oxygen left over. And that is the thing that sort of bonds those two molecules together. And we end up with this sort of structure right here and this bond, and that is again the alpha 1,4 glycosidic bond. You do need to be able to recognize it, and again, how we get there is this is carbon 6, 5, 4, 3, 2, 1. So again, that is where the 1 comes from. Over here, this is carbon 6, 5, 4, 3, 2, 1. And again, that is where the 4 comes from in that linkage. Now, alpha means down, right? And if you look at how this bond is sort of drawn, kind of looks like it's going downward to the oxygen. Yeah, so that's a good way to kind of recognize it. And you'll be able to see the difference. We'll look at a beta bond in a second. Beta looks like it's going up. So alpha, because it means down, it will kind of connect in a downward way between the two. It is only alpha because it is only the carbon number 1 here involved, which is the alpha carbon. Over here, this is the alpha carbon over here, but it's not involved in the bond formation. So that's why we don't use like alpha alpha or anything like that. And that's why there's just one alpha. This is the alpha anomer of the disaccharide for the same reason on this guy way over here on the right. OH group is on the downward circular. Yes, sir. How would the oxygen, are we talking about this oxygen here? Or? Yeah. So this oxygen is bonded to a carbon right here. Yeah. And it's bonded to a carbon over here. And so basically, it's kind of like a dehydration. So originally, they both had OH groups up here. So they both had OH groups. We're going to take water out. And what's left is when that happens, what ends up happening is you're left with, I'll just draw the back part. You're left with an oxygen that is like negatively charged. And on this side, on the other carbohydrate, because it lost like the OH, it's actually positively charged. So what ends up happening is opposite attraction. So they're going to be attracted to each other. And that's how the oxygen kind of sticks in the middle of both of those guys and what ties those two sugars together in that case. Because this guy, you got to remember, also had an OH that left. Yeah. So it lost something that's negative. So it will make that carbon actually more positive when it leaves. And when this guy loses, say, the hydrogen, that's positive. So it's going to make the oxygen more negative in this case. And that's what's going to allow those two then things to be attracted to each other and actually bond and make that and end up making this bond down here is that attraction that happens in that process as those things sort of leave, the water leaves. Uh, that's essentially what's going to happen. So it's a long process to make the water leave. It's just not like water just drops off. So there's a lot of steps that happen in between. And a lot of those steps end up making things more negative, more positive. And again, it gives it that attraction to each other to end up making a bond at the end. Other questions? All right, so this is a alpha 1,4 glycosidic bond. And like I said, you could kind of recognize it because it kind of looks like it's coming down. And again, just think alpha down. And that's definitely, how you can kind of see that. Now, lactose is another disaccharide, and it's made up of a couple of different monosaccharides. It's made up of a beta D galactose and a glucose, either alpha or beta. So basically galactose and glucose here. Same idea. What's going to happen here to make this bond, it is going to end up with a different bond, and this bond is known as a beta 1,4 bond. And again, how we get to those numbers is this is carbon 6, 5, 4, 3, 2, and 1. So that's where the 1 comes from. And again, that is 6, 5, and 4. And again, it's the 1 and 4 carbons that are going to come together here. Same thing's going to happen in this case. We are going to remove water and we're going to be left with an oxygen that's going to basically serve to tie those things together. The difference, though, is when we look at the galactose here, its OH is in the beta form, right? So the OH is pointing upwards. And what happens in this situation is when they, again, take out the water here, they will end up with this beta 1,4 glycosidic bond. And it does look different than the alpha 1,4. And again, you can kind of think of it as kind of going upwards here. And again, that's very similar to what beta means, up. So the alpha 1,4 bond kind of looks like it's coming down. The beta 1,4 bond here, kind of looks like it's going upwards between the two. And again, that's sort of a good way to sort of think about it, is kind of how it looks. And that's it. They do look very different in terms of, how they're kind of connected between them. And here we do end up with, in this particular case, the alpha anomer, as this is, again, the alpha beta carbon over there. Carbon number 1 is where we do alpha or beta, and that is what we end up with over there. Obviously, here it contains this beta 1,4 glycosidic bond. It's found in milk products, and people sometimes have problem breaking that apart, yes, and end up maybe missing out on ice cream and cheese and all that kind of stuff, or not. All right, let's take a look at sucrose, which is the last disaccharide. And sucrose is um, basically table sugar. It's made up of glucose and fructose. And it has a different type of connection here. It has an alpha beta, like the old supermarket. Anyone? Alpha beta? No? Oh, I finally. Oh, erect. There's always somebody. One year I'm going to say like nobody's going to raise their hand. All right, well, this has a alpha beta 1,2 glycosidic bond. And again, let's see how we kind of get to that naming there. And there we go. Maybe. Again, this is going to be 6, 5, 4, 3, 2, and 1. So once again, that is where the 1 comes from. And here, this is going to be 6, 5, 4, 3, and 2. And that is where the 2 comes from. So this connection is different than the last two, as those were between carbon 1 and 4. Here between carbon 1 and 2 is the bond. And this is because it is between a alpha and a beta. So it's between alpha glucose. So this glucose before the bond had its OH pointing down. And this fructose before the bond, I'll put it over here, had its OH pointing up. And that again is why we have both of those symbols, the alpha and the beta, because this is the alpha carbon and that is the beta carbon. And that is where the bond is going to form between the two. So we didn't have those on the previous two because on the second sort of sugar, it wasn't an alpha or beta carbon that we were dealing with. It was just carbon number 4, which is on the other side of it. So this is the alpha 1,2 glycosidic bond, and that is sort of how you could recognize it. It is, again, on both of those sort of alpha beta carbons, carbon number 1 and 2 in this case, at the end. Sucrose is a non-reducing sugar. It is not a reducing sugar, and it's because it has this bond on those alpha carbons, so it doesn't have that OH that's necessary, or the hydrogen that's necessary to be a reducing sugar. Any questions on that there? So again, you do need to know the monosaccharides that make these up. You do need to be able to kind of recognize the glycosidic bonds if you have a picture or something like that. And again, they're pretty distinguishable in terms of how they kind of look. All right, we're not going to draw any of this, so we don't have to worry about it. All right, so for each of these, take a moment and decide what are the 2 monosaccharides that make these guys up. Okay, so for lactose, that is the combo of a glucose and a galactose coming together. And again, we're going to take water out to make that bond. Maltose, which is, I'll just circle it twice, I guess, a couple going on there. And sucrose, the last we saw, and that was our glucose and our fructose, right? And again, this is alpha 1,4, right? This is beta 1,4, and this is alpha beta 1,2 connection happening. So, all right. All right, the next thing we're going to talk about is polysaccharides. And polysaccharides are really just long chains of glucose molecules that basically have been put together. And basically, each glucose molecule that comes together results in the removal of water, basically. So you remove water, they make their glycosidic bond, remove another water, another one gets kind of and stuff like that. So if you have a polysaccharide to kind of make it long chain, you're just going to remove the water, the bond together. Obviously, if you had a polysaccharide and you wanted to break it back apart, you just actually toss the waters back in, and then they would break back apart how they come together. Some polysaccharides we can talk about is amylose, amylopectin, and these are starches that are made of D-glucose. We'll also talk a little about glycogen, which is made of alpha D-glucose, and cellulose, which is made of beta D-glucose. So let's take a look at a couple of these. These are structures as amylose and amylopectin, also known as the potato. Right. So let's take a look here first at amylose. And again, it is just a bunch of glucose molecules basically stuck together. One of the differences between these two guys here is this particular one here is unbranched. So it's just like a straight chain of them. They just line up one right after the other. There is no branching happening like we talked about in organic chemistry where things are coming off of some points or anything like that. It's just a straight chain. You can also see again that kind of 1 and 4 glycosidic bond, which is alpha, once again, kind of coming downward in that connection, just like we saw earlier. So again, that is pretty much your typical looking alpha sort of connection between these guys. And again, it is unbranched straight across. Now, amylopectin is basically the same thing. It is also just glucose molecules together. The difference is there is some branching that occurs. So just like in organic chemistry, at some point, some are going to kind of shoot off and branch off of like the main chain and stuff like that. And because there is some of this branching that occurs, we actually do end up with a couple of different connections that occur here. We still have the one like we did in the other, which is the alpha 1,4 connection basically coming down. And over here, you can see we actually get an alpha, which is from this carbon, 1, and it's going to connect actually to on glucose here. It's going to connect in at carbon number 6, that guy that we usually put like up there on top left of the oxygen. So you're going to have this connection coming down between those, the one here and the carbon number 6, which is going to give us that bond that we see there. Once again, it is still the OHs involved in that bond that happens. As you can see, you still have the CH2 left over that was there. And again, we have our oxygen, that's sort of our connecting point between them. And we get an alpha 1,6 glycosidic bond. This is not an alpha beta bond like we saw in the previous one because, again, it would have to be a connection to this carbon to do something like that. Again, this carbon number 6 is not an alpha or beta carbon. That alpha or beta carbon is always the last one on the right there. So if you don't have the connection between them, you'll just have, one of those sort of symbols, alpha or beta. So again, they're both D-glucose molecules put together once again by removing water. One is branched and one is unbranched in this situation. So amyloids, as we just saw there, is again our alpha D glucose has the alpha 1,4 glycosidic bond, continuous, unbranched. And our amylopectin, as we just saw there, again, branch point there has actually two glycosidic bonds happening, the 1,4 alpha or the alpha 1,6 bond at the branch points. After the branch point here, it just continues back with the alpha 1,4 bonds and then kind of a long chain until maybe it branches out again along the way. Now, glycogen is a polysaccharide. D-glucose, and is typically what is stored when you have excess as we go through glycolysis, and they store that for energy use later on through gluconeogenesis and breaking it back down for energy. It is very similar to amylopectin, but it is a lot more branching happening there. So there's a lot more branch points. Has the same connections as amylopectin. So that's the alpha 1,4 and the alpha 1,6 connection at the branch point, just like it, but just a lot more as well. Now, cellulose is a polysaccharide that has a different connection. It has the beta 1,4 connection. And once again, hopefully you kind of see the pattern here. Beta, again, kind of looks like it's going upwards, like beta is. And like, again, it's kind of going downwards in those connections. And it's the 1,4 connection, again, because that is 6, 5, 4, 3, 2, and 1 in this carbon. That's where the 1 comes from. And 6, 5, and 4 in that carbon. So again, that is where the beta 1 connection comes from in this case. It is glucose units in an unbranched chain that just kind of keeps going straight across. You cannot be digested by humans, so don't need it. It cannot break bonds. Not a good idea there. All right. So for each of these, take a moment and identify type of bonds that we see. Guys, are they branched or okay, so let's take a look. We got our cellulose as we saw at the end there. Again, that's got that beta 1,4 bond, which again kind of looks like it's going the upward sort of direction. We have amylose and amylopectin there in our potatoes. Again, this guy has the alpha 1,4 that looks like it's going down, unbranched in this case. And this guy's got both the alpha 1,4 and also the 1,6 connection that's happening there. And again, that's at those branch points, so it's much more branch. And glycogen has the exact same bonds again, except that it's much, much highly branched more than amylopectin. Any questions on that there? All right. That is chapter 13, they say. Yes. Congratulations. Yes. I'm going to cheer to